Hello and welcome. In this video, I'd like to take a look at our first ATmega328 assembler program. Introduction. Now, before we begin to look at the code, the assembler code, let's take a look at the pinout of the ATmega328. Which is shown here. This is taken out from the ATmega328 datasheet, and along with this pinout, I have also displayed, along with the pins, the Arduino Uno pinouts. So, for example, pin 28, which is port C, bit 5. That's on the Arduino Uno, that's the analog input 5, and so on. Now, I like to particularly draw your attention, to the ports. This is port B, and some of it is here, port C, and then we have port D. That's because we are going to make use of the ports to demonstrate our first assembler program. Now, before we go any further, let me just, from my previous video, extract the SRAM data memory. Now, this is from also taken out from the datasheet of the ATmega328. Now, just a quick reminder, the ATmega328 architecture is based on the Harvard architecture. So it has, what that means is that it has memory allocated for the code. We call it code memory or program memory, and then there is the data memory. Now, this part here that we are seeing here is looking at, is the SRAM data memory. And it's been divided into different parts. First part is the 32 general purpose register. Then next comes the 64 input-output register, and then followed by the 160 extended input-output register, and finally the internal SRAM. Now, I like to focus on these two parts, the 32 register general purpose and the 64 I/O registers. So for the general purpose register, there are 32 as mentioned earlier. Now each register is 8-bit wide. That means, what that means is each register can only store 8 bits. So D0, D1, D3, D2, D3, and so on, right up to D7. And D0 is your least significant bit at LSB. D7 is your most significant bit, MSB. As mentioned a few moments ago, each register, 0, R0, R1, R2, and so on up to R31, they are all 8-bit registers. And these registers are used to store data on a temporary basis. Now, what sort of data are we looking at? Now, these data that is stored in these registers are data to be processed or used by the ALU and so on. Or the data that is stored here could be an address pointing to where the data is found. So this could be the data of two types: data to be used by the CPU, or the data here is an address pointing to the location where the data is stored. Okay, so let's take a look at the structure of an assembler program. I'm going to use this program here to illustrate my points. Now, this is I would say a common structure, and you'll find this structure in other types of assembler program. Obviously, this is for the ATmega328. You'll find similar structure for example, the 8051 microcontroller. They will have similar structure. Now, so let's start with the comments. Now, it is common to have comments because basically comments are there to make it easier for someone to read and understand the program. Now, these comments here, or any comments that you find in the assembler program, they are generally ignored by the assembler or the interpreters. So I'm not going to go into the details of comments. There are different types of comments. So I may do another video on this subject, but for now, we will just like accept this and just to understand that they are there to help us to understand the program and make it easier to read. Now, I personally highly recommend that you add comments to your code. Make it a habit. All right. And I find personally, it takes practice, and you need to persevere. Make it a habit to add in your comments. It is important. Okay, so the next thing I want to look at are the labels. Now, in this program that we are using, there are two labels that I've used. The first one is start, and the other one is end. Now, notice the labels are followed by a colon. Now, for the ATmel Studio assembler, the colons are required. Now, I have noticed that there are some other assembler program that they do not require a colon to be attached to the labels. So you need to check out with the assemblers that you're using. But for our demonstration here, the colons are required. Now, labels like start and end, they are assigned or given an address by the assembler. And basically, these labels or addresses, they mark or indicate the start, the address of where the code is placed. So in this case, for example, start is attached to the LDI instruction here. So LDI space R16, 0xFF, this instruction would have an address that is been assigned to the label, right? So that's basically, I need to talk about the labels. Now, the next thing I want to look at is the things called directives. Now, in this program, I have included this directive that happens to be include. So in this include directive, notice there is a dot or the period attached to it. So the format is a dot or period followed by the name of the directive. In this case is include. So basically this directive, what this directive is saying is that include this file in the program. So this include directive will inform the assembler to include this file during the assembling of the program. So the file that is required here is M328 pdf.inc. Now, this is obviously a file for the ATmega328. Now, very briefly, without going into the details, this file contains information or definition for the program. What do you mean by definition? For example, in this instruction here, out, DDRB. Now DDRB is a register in the IO register which has an address. Now, so the information or the address of DDRB would be defined in this file, so that when you use DDRB in your code, it will be recognized by the assembler. Now, there are two other directives. One is the cseg.cseg and then the .org. Let's take a look at the .cseg. Now, .cseg stands for, the C stands for code, and the seg, S-E-G, is for segment. So basically, it says this defines the code segment. And then for the .org, you probably guessed it, that is the short for origin. So here we're saying that the start address or the origin of the code segment starts at address 0x00. What that means is the code segment starts at hexa 00. 0x here denotes hexa. So we're saying that the code segment will start at that address. And a quick reminder, this is a Harvard architecture, and the code is stored in the code memory, and the data is stored in the data memory. Remember, there's two separate memory in the Harvard architecture. So I think basically that's all I need to say for the directives for now. Okay, so now that the comments, labels, and directives are done, let's turn our attention to the instructions. All right, so here are the instructions highlighted here. So let's look at it. So the first instruction that I want to talk about is the LDI instruction. LDI basically stands for load immediate. All right, so what does this instruction actually do? Basically, it copies 8-bit data into the general purpose registers. So the format basically is LDI RD, K. So the RD stands for destination register. The D, this D here, is a integer between 16 and 31. Remember, there are 32 general purpose registers. Now, only 16 through to 31 allocated or can be used with this LDI instruction. Now, the K here represents the immediate value. Let's take a look at the instructions that is used in this program. So in this program that we are looking at, we have the LDI R16, 0xFF. Now, FF is a hex value. That is because we have defined it here. The 0x here says that this value here is an hexa value. Now, one other thing, the instruction here, LDI, or the mnemonic, notice I've used uppercase and then followed by lowercase. They can be all uppercase or they can be all lowercase. In my preferences, I use an uppercase for the leading character. You don't have to do that if you don't want to. That's entirely up to you. So it's LDI R. Again, the R can be a lowercase, doesn't have to be uppercase. All right, so that means copy or load R6 register R16 with the value hexa value FF. And then the second instruction, LDI R17, 0x01, that basically informs the assembler to say that load this or copy this value, load this value or copy this value 01 hexa into register R17. Next comes the out instruction. Basically, as the in mnemonic here or the word here suggests, that as that's an output, that is to output data. So basically, the out instruction will take a value which is stored or loaded into the general purpose registers and output it or display to one of the I/O registers. So if we take a look at this, out DDRB, R16, basically what this instruction would do is copy or take the contents of R16 and output that to DDRB, register DDRB. Now, as a quick reminder, DDRB is the input-output or the I/O register. The second instruction basically is doing the same thing. What it's saying is out port B, comma R17. That means take the contents or copy the contents of R17 and put it into port B. All right, so that basically that takes care of these two out instructions. Now let me just go into a little bit of detail regarding the ports. I probably would do another video with more details, but for now, a quick reminder: the ATmega328 has 3 external ports. We basically reviewed that briefly at the beginning of this video. There is the port B, port C, and port D. Now, to use these ports, that is port B, port C, and port D, as input or output port, they must be programmed. Now, each port, port B, port C, and port D, they have their own data direction register, DDR, I/O register that is used to make the port as an input or output. So that means DDR or the data direction register is used to either configure the port as an input port or configure it as an output port. Now, in our example, we're using the port as output port. All right, so for each of the port, the quick summary, for example, port B, it would have its own DDRB, and port C would have a DDRC, and port D would have a DDRD. So if you, for example, use port B as an output, then you have to write logic once to DDRB, because once we put logic ones into the 8-bit register DDRB, that will make the entire port as an output port. We would have programmed it as an output port. Now, before I leave this subject here, it's good to remember or know that as you can program the port as an output port, you can also program the port as an input port. For that, you will need to use pin B. Basically, pin here stands for port in pins, right? P for port, in for input. So pin B. So if you want to make port B as an input, then you need to program this pin B register for input. You need to put zeros into this you need to put zeros into DDRB to make it to make port B as an input port. Now we'll come to this in more details in future videos. Then the last instruction of our program basically is a R-jump instruction. What that means is this is a relative R. R stands for relative, and it's a relative jump. Basically, what this do is that it will cause the microcontroller to jump to the target address assigned to the label N. Basically, if you notice in our program, we're saying is keep jumping here. That means it will stay here all the time, right? It's like equivalent to a jumping on the spot. So it'd be staying here all the time. All right. Right. So let's take a look at the program in its entire form. So here the first line says include this file in the program because we need the information in here for this program. We start the thing at the code segment starts at 0x00. That means hexa. The code segment will start at 00 hexa, and then the first instruction is LDI R16 with the value, load the register R16 with the hex value FF. Why FF? Because FF they are all ones. We'll come to that in a minute. Then LDI load immediate with R17 with 01 hexa, and then output the contents of R16 to DDRB. Remember, DDRB is the data direction register. We want to make port B as an output, so we need it to be. We need to program it with all ones. Now, all 8 logic ones in binary is FF in hexa. So that's why we have to load this value FF into R16, and then from R16 we need to pass it on to DDRB to program port B as an output. Now once this is done, then port B is programmed as an output port. So the data that you want to display at port B, we have already put it in R17. So R17 contains 01. So you then copy 01, that is the data stored in R17, to port B. Right, so that means in binary that would be 7 zeros followed by a 1. So the least significant bit would be a 1. Now this program assumes that we have an LED connected to the least significant bit of port B. All right, so and then it comes here and it stays here because we say jump a relative jump end. So basically that's the purpose of the program. Basically is to light up or to switch on the least significant LED attached to port B. So we have come to an end of this video, and in the next video I'm going to put this program that we have used in this video into I will load this into the ATmega Studio and see and examine how and watch how it works using the single step function in the ATmega Studio. So why not join me in the next video, and until then, thank you for watching and see you in the next video. Bye.